Hello students, in this lecture I will discuss linear models of random signals 2. Let us recall a general ARMA PQ model is given by xn is equal to summation ai x of n minus I going from 1 to p plus summation bj v of n minus j going from 0 to q. This is the ARMA PQ model. And we also discuss MAQ model, that is xn is equal to summation bi v of n minus I going from 0 to q. ARP model, autoregressive of order p, that is xn is equal to summation ai x of n minus I going from 1 to p plus vn. The ACF of an MAQ process is nonlinearly related with parameters like this is the relationship Rx of m is equal to summation j is equal to 0 to q minus mod of m bj b of j plus mod of m into sigma v square, where mod of m lies between 0 and q and otherwise Rx of m is 0. The ACF of an ARP process is given by the Ewell-Walker equations, that is a set of linear equation Rx of m is equal to summation I is equal to 1 to p of ai into Rx of m minus I plus sigma v square into delta m. This is for all values of integer m. Particularly we discussed about AR1 process, xn is equal to a1 into x of n minus 1 plus vn, where mod of a1 is less than 1. This is required for stationarity of the signal, and we have seen that this AR1 process is a Markov process. We will consider another example, that is AR2 process given by xn is equal to a1 x of n minus 1 plus a2 x of n minus 2 plus vn. This is a very good example. The properties of AR processes can be studied with the help of this model. Let us see first the linear filter transfer function corresponding to this process. The linear filter transfer function is given by 1 minus a1 z to the power minus 1 minus a2 into z to the power minus 2. So, this is an all pole model, it has 2 poles. The PSD, power spectral density of this process, is given by Sx omega, that is the power spectral density, is equal to sigma v square divided by mod of 1 minus a1 into e to the power minus j omega minus a2 into e to the power minus 2 j omega whole square. So, this is the power spectral density. The ACFs are given by the Ewell-Walker equation. So, we can write down the Ewell-Walker equation, that is Rx of m is equal to a1 into Rx of m minus 1 plus a2 into Rx of m minus 2 plus sigma v square into delta m, that is for all values of m integer. Now, because AR2 process is an all pole model, therefore, for all values of a1 and a2 will not give stationarity. Let us consider the conditions for stationarity of AR2 process. For xn to be stationary, the poles of Az should lie inside the unit circle, that is the condition for stability. Thus, the roots of the characteristic equation, because we can get the characteristic equation by putting the denominator is equal to 0. So, that way denominator was, our Az was sigma v square 1 minus a1 z to the power minus 1 a2 z to the power minus 2. Now, if I put this denominator is equal to 0, then we will get this equation. So, if we put this denominator is equal to 0, we will get this equation. Now, the condition for stability of Hz requires that all the roots of this equation should lie inside the unit circle. Now, roots are given by, there will be two roots of this equation, two roots P1 and P2 given by A1 plus minus root over A1 square plus 4A2 divided by 2. So that if we consider the sum of the roots, P1 plus P2 is equal to A1 and product of the roots, that is P1 into P2 is equal to minus A2. So, we see that A1 and A2 are related to the roots by this relationship. Okay. So, each of P1 and P2 lies inside the unit circle, therefore, we get this quantity, because A1 is nothing but mod of P1 plus P2. Therefore, mod of P1 plus P2 must be less than 2 and mod of P1 into P2 must be less than 1, and in turn these two conditions will imply that A2, from here A2 is less than 1, mod of A2 is less than 1, and from this relationship we get that mod of A1 is less than 2. So, that way A1 will lies between minus 2 and plus 2 and A2 will lies between minus 1 and plus 1. Now, let us consider the particular cases of the roots. Suppose if P1 and P2 are complex, then this part will be less than 0. So, A1 square plus 4A2, that must be less than 0. That will in turn imply that A2 is less than minus A1 square by 4. Now, this region is a parabolic region, and when roots are equal, P1 equal to P2, then this term will be equal to 0, and in that case A2 equal to minus A1 square by 4, which is a parabola. Now, condition 3, if P1 and P2 are real, then both roots P1 and P2, both are magnitude of both will be less than 1. Now, this is the larger root out of 2, this is the larger root, therefore, its value must be less than 1, and this is the smaller root because this minus sign. So, this must be greater than minus 1. These are both real, and from the stability conditions we get this. And from the above two conditions we will get that A2 minus A1. So, if we simplify this condition, A2 minus A1 is less than 1 and A1 plus A2 or A2 plus A1 is less than 1. Two conditions we get considering the real values of the poles. So, to summarize, now AR2 process is WSS if suppose my A1 and A2 must be within this region. So, for real root it should be in this part, for complex roots it should be inside this parabola. So, these are the conditions we get by analyzing the roots of the characteristic equation. And in other words, the AR2 process is WSS if A1 and A2 will lie within this triangular region, then roots will be stationary. And if it lies inside this parabola, then the roots will be complex, and outside this parabola roots will be real. Now, we can plot the ACF and PSD of AR2 process. These are the plots of the simulated AR2 process, and we see that this is a particular case for complex poles. So, the autocorrelation behaves like this, both positive and negative values are there, and power spectrum has a peak. This is a negative side of this spectrum. So, there is a peak corresponding to this point. So, that way if suppose if we have some dominant frequency component in a random process, then we can get it by AR2 spectrum. We will introduce one important concept, that is state space representation of ARP process. That ARP model is xn is equal to summation ai into x of n minus I going from 1 to p plus Vn. The pth order difference equation, this is the pth order difference equation of the ARP model can be reduced to p first order difference equations to give state space representation of the random process. Now, this is an important thing because we have a pth order difference equation, and corresponding to that we can get p first order difference equations, and those will represent the state space equations. Suppose we define Zn is equal to, there are pth order difference equation, therefore there will be p states. Suppose Zn is equal to Z1n, Z2n up to Zpn vector. This is a vector comprising of these elements. Now, each of these elements will be called a state. Now, let us define Z1n to be xn, Z2n to be xn minus 1, and similarly Zpn to be x of n minus p plus 1. So, these p states are defined like this. Now, clearly how these states are related, Z2n is equal to Z1 of n minus 1, Z3n is equal to Z2 of n minus 1, like that Zpn is equal to Zp minus 1 of n minus 1. So, we have a difference equation relationship between state variables. We can also rewrite xn is equal to summation ai x of n minus I going from 1 to p plus Vn as, now we will substitute these state variables corresponding to each of the terms. We get Z1n is equal to a1 into Z1 of n minus 1 plus a2 into Z2 of n minus 1 plus up to ap into Zp of n minus 1 plus Vn. So, this equation now Z1n is this, similarly Z2n is Z1 of n minus 1, Z3n is equal to Z2 of n minus 1, etc. This can be rearranged. Rearranging the equations, we get Z1n is equal to a1 into Z1 n minus 1 plus a2 into Z2 n minus 1 plus up to ap into Zp n minus 1 plus Vn. So, this is the representation for the first state. Similarly, Z2n is equal to Z1 of n minus 1, Z3n is equal to Z2 of n minus 1, etc. and finally, Zpn is equal to Zp minus 1 n minus 1. So, that we can now write Zn, this is a Zn state vector Zn, which comprises of elements Z1 n, Z2n up to Zpn. That is the Zn vector, it is a column vector, is equal to A matrix times Z of n minus 1 vector plus B matrix times Vn. Vn is a scalar only. So, where A is given by this matrix now, it is a P by P matrix. First row is A1, A2 up to AP. Second row is first element is 0, then 1, and rest of the elements are 0, and similarly last row is 0, 0, last element is 1. So, this is the A matrix. These equations we are writing in terms of A matrix equation. And similarly, B matrix is given by 1, 0, 0, rest of the elements are 0, transpose of this row vector. So, that way we will get a column vector here. We can also write xn in terms of Zn. Suppose if we have to write xn in terms of Zn, then we can write xn is equal to actually Z1n. So, that way if we write C is equal to 1, 0, 0 up to 0, all the remaining elements are 0. If we consider C to be this matrix, this is a row vector actually, then xn will be C times Zn. So, that way we can get suppose xn is equal to c times c is now 1 0 0 like that 0 into zn vector. Zn vector is z1n like that up to z of pn. So, if we multiply these two matrices, we will get xn is equal to z1n. That is exactly what we have shown earlier, z1n is equal to xn. That way we can write xn also, that observed data also, in terms of state variable, that is c times zn. This model is known as the state variable model, and this equation zn is equal to a into z of n minus 1 plus b into vn, this is known as the state equation, and xn is equal to c times zn, that is known as the observation equation. We shall consider one example, that is AR2 model. Xn is equal to a1 x of n minus 1 plus a2 into x of n minus 2 plus vn. This is the AR2 model. How to get this state space representation? There will be two states, one is xn and another one is x of n minus 1. This state space representation is given by now. There will be two state vectors, zn is equal to a into z of n minus 1 plus b into vn, where n xn, that is the observed data, is equal to c times zn. Then what is A matrix, where A is equal to a1 a2 0 1, this is a 2 by 2 matrix. B is 1 0 transpose and C is 1 0, this is a row matrix. So, that way get this state space representation corresponding to this difference equation. So, this is a second order difference equation that we have converted into a matrix first order difference equation. Though the number of states is 2 here, we can define the state variable representation in different manners. There are different ways to represent state variables, but this is the model we will be using. Let us consider the ARMA PQ model. Under the most practical situations, the WSS process may be considered as an output of a filter that has both zeros and poles. So, MA model and AR model are particular cases. In MA model we have only zeros, in AR models we have poles, but most generally we will have both poles and zeros. The filter transfer function corresponding to ARMA PQ model is given by Hz is equal to, this is the relationship, ratio of summation bi z to the power minus I going from 0 to q divided by 1 minus summation I going from 1 to p of ai into z to the power minus I. This is the transfer function corresponding to a ARMA PQ model. The model is given by xn is equal to summation I going from 1 to p of ai x of n minus I plus summation j going from 0 to q of bj v of n minus j. This is the difference equation model for the ARMA PQ model. That filter Hz has both poles and zeros, and stability is determined by poles only. Therefore, the AI parameters determine the stability of Hz, and hence the wide sense stationarity of Xn. So, Xn will be WSS under certain conditions on AIs. PSD and ACFs of ARMA PQ process. The PSD is given by Sx omega. Sx omega is equal to, this is the mod of the numerator term square divided by mod of the denominator term square. Sx omega is given by this ratio, that is equal to summation I going from 0 to q bi e to the power minus j omega I whole mod square divided by 1 minus summation I going from 1 to p ai e to the power minus j omega I whole mod square. So, this is the value for Sx omega. This is the expression for Sx omega. And here in ARMA PQ model, we consider from j is equal to 0 to q, therefore, there is a B0 V of n, and this B0 absorbs the variance of Vn. So, that way Vn will be considered as unit variance, so that its variance will be taken care of by B0. So, this B0 here there will be an expression, suppose there will be B0, V0 will be there, and this V0, B0, V0n will be there, and this V0n is now unit variance, because variance of the white noise process will taken care of by B0. So, that is why we do not have any sigma V square term here. The ACF of the ARMA PQ process is given by this expression x Rx of m. By definition, it is equal to E of xn into x of n plus m. Now, we will be writing x of n plus m in terms of the difference equation model. So, that way we will have this summation I going from 1 to p x of n plus m minus I. That way x of n plus m will be written plus bi's will be there. Okay. The ACFs of xn are given by this expression Rx of m is equal to E of xn into x of n plus m. Now, we can write x of n plus m, this we can write as x of n plus m is equal to summation ai x of n plus m minus I going from 1 to p plus summation b I n plus m minus I going from 0 to q. We are expanding x of n plus m. Then this autocorrelation function will be given by summation I going from 1 to p ai into E of x of n plus m minus I into xn plus summation I going from 0 to q of bi into E of v of n plus m minus I into xn. So, this is the autocorrelation function of xn at lag m minus I. So, that way we can write summation I is equal to 1 to p ai into Rx of m minus I. This xn and x of n plus m minus I. So, their difference is m minus I here, and plus summation bi into E of v of n plus m minus I into xn I going from 0 to q. So, this is the expression for autocorrelation function of xn. Rx of m is equal to this, and we see that there are these bi terms are contributing to this expression, but we note that xn is a function of past Vn's and are uncorrelated. So, that way xn is uncorrelated with future Vn. So, suppose xn and some future any future Vn, for example, Vn plus 1, Vn plus 2 etc. uncorrelated, because xn is generated due to the earlier Vn's. So, that way we can write E of v of n plus m minus I into xn is equal to 0 if suppose this quantity is greater than n plus m minus q is greater than n. Okay. So, this term is greater than this. So, in that case we get m is greater, if m is greater than q, then this term will be equal to 0. Therefore, for m greater than equal to q plus 1, we will get this equation R x of m is equal to summation a I into R x of m minus I going from 1 to p. So, this is for values of lag greater than equal to q plus 1. So, this is a set of Walker equations. We can consider one example. Suppose ARMA 1 process, the model is given by xn into a1 x of n minus 1, that is the AR part, plus b0 into Vn plus b1 into Vn minus 1. Now, here the condition for Whitesand stationarity will be determined by the A1 parameters like AR1 process. So, mod of A1 should be less than 1 for Whitesand stationarity of xn, and the PSD will be again given by this expression, but here sigma v square we have already taken sigma v square is equal to 1. So, that way this sigma v square will be equal to 1. So, that way we have Sx of omega is equal to b0 plus b1 into e to the power minus j omega whole mod square divided by 1 minus a1 into e to the power minus j omega whole mod square, and for omega lying between minus pi and pi. This is the expression for power spectral density. HCF of ARMA 1 process. The HCF autocorrelation function is given by Rx of m, that is E of x of n plus m into xn, and using the previous relation we can write this is equal to a1 into Rx of m minus 1 plus b0 into now E of v of n plus m into xn plus b1 into E of v of n plus m minus 1 into xn. Now, Rx of 0 from this equation, this part we can write Rx of 0 is equal to a1 into Rx of minus 1 plus b0 square. So, this part b0 again when m is equal to 0, suppose when m is equal to 0, then this will be Vn into xn, and this will contribute b0 into Vn square. So, that way we will get here b0 square. Similarly, Rx of 1 will be equal to a1 times Rx of 0 plus b1 b0. That way we will get Rx of 1, and these two equations, Rx of 0 is given by this, Rx of 1 is given by this, they can be solved to find out Rx of 0 and Rx of 1. For m greater than equal to 2, now we will have the Walker equation, that is Rx of m will be equal to a1 times Rx of m minus 1. So, that way we can get the remaining autocorrelation functions like Rx of 2 we can get Rx of 3 etc. we can obtain. How to fit an ARMA PQ model? So, given the autocorrelation functions, we can find the model parameters of an ARMA PQ process. So, because of the relationship between the autocorrelation functions and the model parameters, we can find out the model parameters. The autocorrelation functions are estimated from data. Generally, autocorrelation functions will be estimated from the data, and those autocorrelation functions are used to estimate the model parameters. ARMA PQ is more economical model. Economical means it is less number of parameters. Only ARP or MAQ model may require a large number of model parameters. Suppose if I given data, if I try to model by MAQ model, then this may require a very large value of Q. So, only ARP or MAQ model may require a large number of model parameters to represent the random data adequately. Suppose given random data, if we try to fit only ARP or MAQ model, they may require large values of P and Q. And therefore, if we use a ARMA PQ model, then P and Q need not be very large. This concept of model building is known as the parsimony of parameters. We should be parsimonious in selecting the parameters, so that P and Q should be as small as possible. We will broadly describe the ARMA PQ model building steps. First step is identify the model order parameters P and Q. After P and Q are identified, estimate the model parameters AIs and BIs. Check for the modeling error. If suppose we will find out the difference between actual sample value and the value predicted by the model. If it is white noise, then stop. So, model building is over. Else select a new values of P and Q and repeat the steps 2 to 4. So, that way we can build an ARMA PQ model. Though this is a quite involving process, in a nutshell these steps can be described as this. So far we have discussed how to model WSS random process, but most of the practical data are non-stationary. Operations like differencing, logarithm, etc. may be performed to make data stationary. There are different ways to make data stationary. Two such models for non-stationary data are: first one is ARIMA model, autoregressive integrated moving average model. Here the difference data xn minus xn minus 1 can be modeled as an ARMA model. After differentiating, this data will be fitted into an ARMA model. That model include integration, therefore, after differentiating it is becoming ARMA model. Seasonal ARMA, that is SARMS ARMA model. Here signal contains a seasonal fluctuation terms, for example, weather data. The signal after differentiating by a step equal to the seasonal period, that is P, becomes stationary, and ARMA model can be fitted to the resulting data. So, xn minus xn minus p. So, this difference data can be fitted to an ARMA model, that is the SARMA seasonal ARMA model. So, these are some of the ways to deal with non-stationarity, but we will not discuss this in details. Let us summarize. An AR2 process is a typical example of ARP process. So, we discussed how to analyze this AR2 process, stationarity of the process. AR2 process is a typical example of the ARP process. We discussed how to analyze the AR2 process in terms of stationarity, autocorrelation function, power spectral density, etc. This state space representation for an ARP process is given by Zn is equal to A Z n minus 1 plus B V n, where A is a P by P matrix given by this. This is the AR parameters A1, A2 up to AP, and the rest of the rows will contain 0 except 1, 1. So, there will be 1 in one place and remaining place it will be 0. So, this is the A matrix. Similarly, B matrix we can find out B equal to 1 0 0 up to 0 transpose. So, this way we can write Zn is equal to A Z n minus 1 plus B V n. This is the state equation. Similarly, we have the observation equation. So, this data xn can be written as C times Zn, where C is the row matrix, Thus, ARP process is a vector Markov process. So, because this is a first order in terms of the state variable vectors. So, this is a first order. In terms of vector, it is a first order AR process, and therefore, it is a vector Markov process. We discussed about ARMA PQ process. The difference equation model is given by xn is equal to summation ai x n minus I going from 1 to p plus summation bj v n minus j going from 0 to q. This is the ARMA PQ model difference equation. Autocorrelation function is given by Rx of m is equal to, this is the expression summation ai Rx of m minus I going from 1 to p plus summation bi e of v of n plus m minus I into xn I going from 0 to q. And for m greater than equal to q plus 1, this autocorrelation expression will result into Ewell-Walker equations given by Rx of m is equal to summation ai Rx of m minus I going from 1 to p. And power spectral density is simply given by this expression Sx omega is equal to summation bi e to the power minus j omega I whole mod square divided by 1 minus summation ai e to the power minus j omega I going from 1 to p whole mod square. This is the expression for power spectral density for ARMA PQ process. And we also discussed very briefly about model building, and the parsimony of parameters play an important role in ARMA PQ model fitting. Thank you.